everybody that you did a good job on this second exam, and you made me and yourself proud. Most of the grades were very good, and I think you spend more time this time, and exam 2 was harder than exam 1 because deflection plus the other part was a little harder than the first section with the bending moment and shear for the beam. So, and you did more study, you solved more example, and most of you guys contacted me during the past few weeks before the exam, and I knew that you will get much better results, and you did it. And please do not stop this hard work. Just keep going, keep doing this, and you can see better results. And without any, yes.
How many questions was the second exam worth?
2.
2?
How many sections? What do you
Oh,
mean?
no. How many points was the exam worth? I'm
25.
sorry.
25.
Okay, for an email you sent me, you put my score out of 20.
No, but it's from 25. Yeah, maybe I'm mistyped, but all the grades were from 25. Sorry about that. From 30, I made another mistake because I had 2 exams, one for you guys, another for earthquake engineering for master, and they had 25. You had 30, so I just confused sometimes with those numbers. But your grade were from 30. So any grade that you saw, it's from 30. So you did very good job, and the average was much higher than the first grade, first exam, and especially most of you guys, you did much better than the first exam. So if you keep doing this, you will be great at the end. And believe me, I believe on all you guys. And I think if you go after hard work and do your job, then you can see the average was about 19, because we had 2 or 3 bad grades, so it brought down the total average. But most of the grades were very much better than the first exam. So I believe on this. If you want, you can compete with good schools. And this is my point. I want to do something, and I want to ask you to do something to be able to not to afraid from good schools. If somebody asks you, okay, can you compete for example, with MIT? Can you say yes or no? It's up to you. If you go after this stuff, for sure you can say yes. No, nobody got 100, but we had 29 of 30. Yes, we had 29 of 30. We had a lot, more than 20. So that was perfect. We had 18, 19, 20, 22, 24, 25, 26, 29. So very good grades. So yes.
Could I take a look at my test and score after class? Because
Sure. Yes.
Okay, because I remember last week you said the total points we could get was either 20 or 25. Since we only had 2 questions.
Yeah.
Okay.
No. But the grades actually, those are from 30. I can talk to you. Yes, after class, after lab. After lab, please stay. I will go through your exam.
Okay. Thank you.
Okay. You're welcome. So please do something to prepare yourself for showing yourself that you can compete with very good schools, with very high ranked students. Do it. You can do it. Yeah. Please keep doing good work. And for the final exam, we have columns, short columns and long columns. plus one or two more chapters from the past. I will give you those chapters for the finals. So please just keep doing this. Review the examples, go after the homeworks. If you have questions on homework, ask me, and we will go through the answers. And for sure, you can do better and better by doing this stuff. And another thing, in all the exams, especially on online, nobody can see what you are doing. Yeah, so it's you and you. So hopefully not. But if somebody likes to cheat, so you can do. Nobody can see you. Nobody actually do something to uh, check you for that part. But at the end, what's the point? Do you know what I mean? So you want to get good grade with no knowledge for what? To do what? When you can use that knowledge. So why you spend your time not to learn anything, just get good grade, and after that just put your degree and go after another work because you don't know anything about this? That's not wise. Yeah, we are adults. We know that why we are here, and what do you want to do? What we want to do? Go after your big goals. Go after big goals. With your knowledge, you can help a lot of people stop uh, actually destroying all the structures during earthquake. With your knowledge, you can stop it. So it can benefit you and the people. So this is our responsibility. And because of that, I want you to go after hard work. Do not accept good grade with not that much work, with not that much knowledge. Okay, today I'm going to continue this column. Column as you can remember for the short column, it means that the buckling is not important. Yeah. So you can load all the way to get to the maximum load to Fy. So because of that, we call that short column. Yeah. So because we can go all the way to the final load without any buckling. So up to now, we went through the column with just rebar at the corners. Yeah. Nothing between. So if we have rebar everywhere, how can we find the PN, means nominal axial load capacity, and MN, nominal moment capacity? How can we do that? That's the example. And right after this, I gave you one homework, and just follow this instruction. Try to understand this. Then you can do it fast. Okay. We have a short column, and it has rebar with this actually uh, distances between. Yeah, that's we know this stuff. F prime C 6 ksi and Fy 75 ksi. And we consider that the neutral axis is equal 18 inches. Yeah. Why we are checking this? Because in future, like last week that I mentioned, we are changing C below and above the that balance point, and then we can plot that diagram. As soon as you have to that diagram, you don't need to do anything. Just use that diagram for that percentage of the rebar for any column to check if it's inside on that or outside. So today we are going to learn all this stuff with the ACI diagrams, and you can plot that by yourself as well. So we want to find the capacity, and we know that we use number 11 rebar. So we call that, look at this, AS1, we have 3 number 11. AS2, we have 2 number 11. AS3 and AS4. And this is the center of the column, and PN is here, means eccentricity is at this side. So the side of the column parallel to E, we call that H. Doesn't matter if it's greater than this side or smaller, doesn't matter. We call that H, and this side B. Okay. So everything here is clear, and we have the cover to the center. Everything, all the information we have. AS for each number 11 rebar 1.56. Okay. Start with a strain diagram always. And this is your C. Look at this. C is neutral axis. Difference between neutral axis and CL. We know that. So in this case, as you can see, that from to the right side of the neutral axis, because we have load here, at this side, at the E side, you have compression. Other side of the neutral axis, we have tension. That's it. So you can see from here to here is 18 inches. From this rebar to the end is 7 plus 2.5 means 16.5. But this is 18. So it means that epsilon S3 means for this rebar is in compression, because this side is in compression. When it's compression, we know that a compression for the concrete should be 0.003. That's epsilon U for the concrete. Okay. Then write the equation to find epsilon S1, S2, S3, and epsilon S4. We know those are in compression, so we can call them epsilon prime S1, epsilon prime S2, epsilon prime S3, and epsilon S4. Doesn't matter. So see which one is good for you. But if you see either one, it will give you the information that you want. Yes, what's the question?
What was that point PN again?
That's the location of the point load. It means that the load is not at the center, so with no eccentricity. It means that this column, that's a plan view of the column. This column has a load Pn plus a moment Mn. What's that moment? Moment is Pn times E. Can you remember from last week? Let me show that. Consider we have a column. That's a column. Yeah, that's to the footing. Yeah, that's the elevation view. So that's the center line of the column. If the axial load is here, you have no eccentricity. Eccentricity is equal to 0. So in this case, you should show Pn here. But if load is this side, as you might remember, if we have Mn and Mn and Pn, that's the axial load. Imagine we have both of them. Yeah. So in this case, I can show this like something else. I can show this like a column with this axial load on the center line, and I can show this Pn. It can be whatever the distance is, with eccentricity equal E from the center. And this load is Pn. Yeah. If you check the slide from last week, you can see that. So your Mn is equal Pn times E. Pn times E. Yeah, that's it. And how can I calculate E? E is equal, from this equation, is equal moment divided by axial load. Yeah, and that's it. So it means that whenever your column has moment, you can show that like this, show the axial load with eccentricity. That's it. Is that clear now?
Yeah, thank you.
Perfect. Okay. So let's go after the other part for this case. Uh, we have to find the epsilon for all the rebar. Yeah. Then epsilon for all the rebar, based on the epsilon times E, modulus of elasticity for the rebar, you can find the force. Yeah, you can find the stress. A stress times the cross-sectional area. Over here, you have 3 number 11. Epsilon times E for this one times 3 number 11, you can find CS1. Look at this. Then epsilon S2 times E times AS2, you can find CS2. Do the same for this one and that one. But the last one is in tension, yeah, because at the tension part of the strain diagram. So it should be TS4 is equal epsilon S4 times AS4. AS4 has 3 number 11. So we have to find CS1, CS2, CS3, and TS4. If this one was at this side, we show that with T. Because it's other side, we show that with C, means compression. And the concrete is in a compression as well. And as you know, A is C times beta 1. So we have to calculate beta 1 times C, you have A. Because we know C, you can find A. And this side is 0.85 F prime C. And the other side, this is the cross, based on the cross section of the area of the column. Yeah, if I want to show this, that's it. So this concrete block is something like that. Let me answer the chat. Can you repeat the equation for CS1? Yes, the equation, remember from strength of material, stress, yeah, is equal epsilon times modulus of elasticity. Yeah, so we know the epsilon. We are going to calculate this. We know epsilon times ES. We know ES. ES is 29,000 KSI. So we can find a stress. Then force, if because it's compression, I show that with CS. CS is equal stress. Yeah, that's a stress. Yeah, this one times cross sectional of rebar area AS. Okay, so if I'm looking for F1, so I have to find epsilon S1, yeah, and if it's better to call it FS1. Then FS1 times AS1, you can calculate CS1. If I go with FS2, epsilon A S2, so I can calculate CS2 based on AS2 and FS2. Yeah, so this cross-sectional area times a stress at this point. A stress is epsilon times ES. Epsilon times TS times that will give us this force. Then all the forces. And this force will act at the location of this rebar, yeah? At the center, somewhere at the center. Then the other one will act here at this side. Then the other one at this location, the other one at this location, in tension. So, but in one cross section as like this, you can see just one line, but this force is on the whole cross section of that column. I hope this is clear for you guys, because it's the same as the beam, yeah? But this is vertical element, that was is horizontal element, just the difference between these two. So what should we do? We have to find the forces and go to this, and based on the equation that we have for Pn and Mn, calculate Pn and Mn. So did I give you the answer?
Yeah.
Okay. Yes. Okay. So thank you. I saw your text. Perfect. So let's go and find those parts. Yeah, I'm going to find epsilon 1. Start with epsilon 1. So over here, I call them epsilon prime because they are in compression, but doesn't matter. Yeah, you know, this is at the compression part. 1, 2, 3 in compression, 4 is in tension. So I rename them epsilon prime to make that more clear. Okay, what's the equation for epsilon prime in this diagram? Always for compression, this is their equation. Epsilon prime S is equal to epsilon U C minus D prime divided by C time and F prime S for this bar is epsilon u, that's actually this one, epsilon u times this means epsilon prime s times es. So epsilon prime s es, and must be less than or equal fy. If it's greater than fy, as consider that equal fy. If it's less than fy, consider that whatever it is. And in this case, we are using very high grade and expensive rebar fy 75 ksi. Yeah. So let's start with this equation and find these parts. Okay, I named them. Look at this. For AS1, D prime is here. For AS2, we are going to use this equation. I named them, and just you remember how to use them. Yeah, name them correctly and use them correctly. So for AS1, D prime is here. For AS2, D prime is here. Why D prime? Because these are compression bars. AS3, D prime is here. AS4, D4, because it's in tension. And I changed them to make that more clear. 1, 2, 3 in compression. So I call them D prime. 4 is in tension. The solution here is not exactly the same as the solution in the book. So I think this one is more clear. Otherwise, you have to jump from this side to that side to calculate those numbers. I think if you concentrate on this one, understand this, then go to the book and read that one, you can understand that as well. Yeah. Otherwise, yes.
So like for all the listed givens, you put primes there just to know that what we're using is in compression rather than us getting confused if it might be in tension.
That's correct.
Okay.
That's correct. First of all, show the neutral axis and all the rebar at the right side, because we have moment this side. Yeah, you have moment at this side. If you have right side, you have in compression. The other side, at the E direction. Just remember, always at the E direction, all the rebar at after neutral axis are in compression. Other side in tension. So I can see two raised hand. What's the question?
Mine is, how do we determine which side is compressive and tension? If you could repeat that again.
Perfect. Look at this. We know the load is here. Yeah. So when you load, the load is here, this side is in compression. The other side is in tension. That's it. That's very easy.
Thank you.
Okay. So any other question?
If the load, sorry.
I was just gonna say, what if the load was in the middle, like in the center?
Yeah, that
So
was.
if the load is at the middle, there is no eccentricity, there is no moment. So it should be the first equation. There is no need to calculate anything. The capacity of this should be 85 F prime C times B times H, yeah, plus AS times FY. That's it. There is no need to calculate anything. When you have moment, you have to find this stuff. Otherwise, it should be short column without eccentricity. That's the first part that we went through that 2 weeks ago when we started this. Yeah. So that's the easiest part. So there is no eccentricity. When you have eccentricity, then you have to go and find compression, compressive rebar, tension rebar, and do whatever we are doing here. Is that clear?
Yes, thank you.
Okay. So right now we know the distances. Look at this. D prime 1, 2.5, because it's here. D prime 2, 7 plus 2.1 means 9.5. D prime 3, 7 plus 7 plus 2. Look at this. All these numbers you can pick from the this picture. Then put all these numbers, because we know D prime, you know C. C is 18 inches. You know epsilon U, 0.003. With this D prime, you can find epsilon prime S1, 2, and 3. That's it. Then this one times ES 29,000, you can find F from S. That's the same equation. This times ES. So this number times ES times ES times ES, you can find stresses. And must be less than FY. FY was 75, it's less, so keep this. less, keep this, less, keep this. If it was 75.6, you should consider this 75. You shouldn't go more than that. Must be less than or equal F5. That's it. As you can see, it's very easy. This from strength of material. Yeah, just find the number, the distances, go to the equation for the compression and find the stresses. Then go for the tension. For the tension, the epsilon is like this. This is the equation, D minus C divided by C. What is D? I show that we have just one D, one rebar in with D, 7, 7, 7, 2.5, 23.5. Go to this equation, we know C equal 18, then times ES must be less than FY 75, so it's good. So keep this. That's it, we are done. Then with the stresses, find the forces, because these are stress. Yeah. How can I find CS1? Look at this, CS1 means stress times total area of the rebar at this location. We have 3 number 11. 3 number 11 means 4.68. Area times stress. Stress 74.8. Look at this. Stress at this point was 74.8. We have 3 number 11, 4.6. So stress 1 times AS1 will give us CS1. Do the same for CS2, but in this case, we have 2 rebar. That's it. For CS3, we have 2 rebar. 2 rebar. That's it. We are done with this. So we calculated all the forces, compression forces in the rebar in compression zone. Then we have to calculate total force for the concrete. Let me back to this one. Have rebar in compression plus concrete in compression. Then we have rebar in tension. We might have 2 layers of the rebar in tension, or 3 in tension, 1 in compression. Doesn't matter. As soon as you know the location and you know that's upward or downward, show them correctly and then follow the instruction that I'm giving you here. Yeah, that's it. It's too easy. Just try to follow this and understand. And if you have question, ask me to make sure at the end of this class you have no problem solving this problem, this kind of homeworks. So how can we find beta 1 from the equation that we have for F prime C equals 6 KSI? KSI, if you go to that, you will get 0.75. And C is 18. What's the equation? The equation is 0.85 F prime C A, B, always. That's the equation always we have. That's good for beam as well. Exactly the same as the beam when you are bending. So what's the A? A is beta 1 times C. We calculated beta 1, so we can calculate A. What the B is perpendicular to the eccentricity. We have eccentricity at this direction, so this is your B, 12 inches. A, 13.5. FRMC, 6 KSI, 0.85. That's your total C. Yeah. So as you can see, let me show this one more time here. Total of this will sit at the A over 2, somewhere out here. Have another compression from concrete, 3 compression from the rebar, 1 tension from the rebar. Okay. So far, we calculated all the tension and all the compression and for the concrete and the rebar. What about the tension in the rebar? Tension, always we have go with the same equation. AS, we have AS4, 1, 2, 3 rebar. So 4.68, 3 number 11, times FS. FS4 is 26.4. Plug it in here. That's it. Do the same. But when you want to show them, show the tension opposite direction. Compression, for example, this direction. Yeah, because you are pushing downward. So this is critical to show them correctly. Compression will go down, 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 and tension upward. Yeah, and we have another for the concrete as well. Okay, so how can I write find the Pn? Always Pn is like this: total C. This is not neutral axis. This is force. Means this one. Total force coming from the concrete. Okay, should be downward because it's compression. Downward plus CS1. Look at this, downward plus CS2 downward plus CS3 downward. If this one was upward, forget about that one. C, compression concrete, CS1, CS2. If we add just these two, but here this C is at this side, we have three rows of the rebar under compression. So we will go with all the compressions, add together, minus all the tension. Over here we have one tension. And we calculated all these forces. C, 826. C1, if you go to this one, CS1, 350. CS2, 129. CS3, 23. Minus T, 124 kips. That's your nominal axial load capacity. This column can carry this much load for axial load. That's it. Then how can I calculate the moment? Look at this. That's the equation for the moment. Forget about that one in the book. This is actually, I just cut and paste from the book, but I will go with this, and then you will learn how to use this one as well. If you follow this, because it's based on this type of actually dimension and letters that I consider. So for the concrete part, always concrete part, C means this C times H divided by 2 minus A divided by 2, or H minus A divided by 2. Both of them are correct. Yeah, because we are taking moment around the center line. This is important. Moment around center line. So the concrete over here, we have concrete with the A. You can remember we had compression with A. So at the center of that, we have compression for the concrete downward. Yeah, let me add this. It was better actually to have that force. I don't know why I forgot to show that here, because it's to have force like this, capital C. This is this force. Not this is force, is not distance. So this is for compression. What's the distance from here to here? Okay, we know that this is A over 2 because the total was A. This one will go at the center of that, so A over 2. From here to there is H over 2 because that's a center line. H over 2 minus A over 2. So C times H minus A divided by 2. That's it. As you can see, very easy to understand and follow this with this actually picture. Then go after this one. Look at this. That force will create moment at this direction. Okay, I consider that positive. Then this one will go at the same around the center line. Look at this. This one will go at the same direction, so positive. So CS1 times what's the distance from here to here is H over 2 minus D prime 1. Look at this. H over 2 minus D prime 1. Very easy to understand. CS2, what's this one? Around this will create moment at this direction again. This one, because those are at the same direction as the concrete create moment. So we will add to that one. So CS2 times this distance. What's this distance? H over 2 minus D prime 2. That's it. Do the same for this one. As you can see, this one is other side. So it will create moment at opposite direction. So this is, you must make decision if you go with the positive or negative. Or in this case, I made that easier for you guys. Go with the positive, then go with the sign. So I went with this, that for CS3, yeah, CS3, you have negative, okay, negative, that's correct. This CS, what's the distance from here to here? Here to here. because d prime 3 is bigger than h/2, I will write d prime 3 minus h/2, means distance from here to here. As you can see, minus cs3 times d prime t minus h/2. As you can see, the final must be negative moment because it's opposite direction. You can do with any other method that you think it's easier for you, but at the end should be reduced, it should be deducted from this moment because it's opposite direction. Okay, so we are done with the compression concrete, compression rebars, and we have just one more left. As you can see, this one will create moment at the same direction as concrete. So we consider that positive. Positive TS4. What's the distance from here to here? Yeah. What's the distance from here to here? I can go D4 minus H/2. Yeah. So you will get distance from here. That's it. Just plug in numbers. All the numbers that you have here for C, CS1, H, A, D prime 1, D prime 2, D, just plug in the numbers. That's it. And you can find the final answer. And because everything is inch and kips, you will get kip inch divided by 12, you will get foot kip. That's it. That's the nominal moment capacity, and that's the axial load, nominal axial load capacity. So is that hard? Any question on this one?
I have a question.
Sure.
How do you know what the D prime values are?
Okay, D prime, let me show that to you. We calculated them here. Look at this. This is D prime 1, D prime 2, D prime 3, D prime 4, D4. Is that clear?
Professor, I think one of the things I noticed for like D4, since it goes past the neutral axis, that bar becomes in tension.
Sure. When you have a load at this side, means eccentricity parallel to the C. In that case, anything other side of the C should be in tension. The rest should be in compression.
Okay.
Clear?
Yeah.
Perfect. So as you can see, follow this instruction. I try to make this as simple as possible with following just from one side. Yeah, instead of measuring from this side and that, so it doesn't matter. You can measure from this side to find distance from center line to this, or center line to this one. You can do from any other direction that you want. But with this method, you will measure from one side always. Maybe it's easier. So hopefully it's easy for you guys to follow this and understand. And at the end, for the spacing of the tie bars. For tie bars, for shear reinforcement for the column, as you might remember, maximum tie bar spacing is minimum of these three, 16 times of the diameter of the main bar, number 11. Diameter is 1.41, 16 times of that. 40 times of diameter of the tie bar. We assume tie bar number 3, means number 4 for here. Use number 4 tie bar. So number 4, 48 times of that. Number 4 tie bar diameter is 4/8, 4/8. So 24 inch. And a smallest dimension of the member was 12 times 26. A smallest dimension is 12. So between those three, pick the minimum of these three. So use number 4 at 12 inch. This is the minimum required tie bars. You might go with a smaller than this, but you can't go with more than this. You can't go with 16 inches, but you can go with 10 inches, 5 inches. Yeah, not more than this. Okay, but let me go after this to give you some more information. These informations are for those that they want to compete good schools. And I think all of you want to do that. Yeah. So can we see the designer made good decision on this picking 75 KSI rebar, very expensive KSI rebar? Is that a good decision or not? How can we catch that? Look at these numbers. Just this rebar got close to 75. Look at this. The rest is almost half, nothing almost, even tension is too low. So it means that that wasn't good decision to go after this kind of rebar with high strength, with expensive, the price that the homeowner should pay for that, and get almost nothing, 1/12, yeah, 1/4 of the rebar will reach almost close to that. 75% of that is too low. So that's not a good decision. It's better to change the actually rebar installation or change the FY for the rebar. As you can see, this is not good decision. And you can check that with the stress in the rebar to see if it's acceptable or it's not that good idea. Okay. Circular column. This is good for those that they want to compete with other schools. What can I do? How can I do with this? How can I do this? Do the same. No difference. Look at this. D1, D prime 1. Here is neutral axis. So this side is in compression. The rest are in tension. So you can see CS1, CS2, C for the concrete in compression, TS3, TS4, tension, tension, compression, compression, and compression. That's it. Then go with this. That's the neutral axis C. You know the C. Go with epsilon prime S, epsilon S for tension and compression. The same as before. Nothing is changed. The only change is how to calculate the area of this part of the circle. That's it. Because A times B is the area of that part. 0.85 F prime C AB. Over here, you know A, but there is no B. What's A and B? A and B is the area of the concrete under compression. So find the area of this part that is under compression. Let me answer a chat. Why is the load distribution on the less than half of the column? It depends on the eccentricity. When you have huge load, huge eccentricity, you will get a small part of the column under compression. The rest will go on the tension. If there is no eccentricity, so the load should be here and at the center. So everything concrete and the rebar should be under compression. As soon as you get moment, you will put part of the column under compression, another part under tension. If you have huge eccentricity, sometimes if you are going to show E, point load will go off the concrete. It means that moment is huge. Moment divided by P, it will give you the eccentricity. Yeah. So based off that, you can actually find the C. You know the C, and then based on the C, you can consider what rebar is in compression, what rebar is in tension. That's it. How can you calculate this part? I will ask you guys, if you like, go and learn. Yeah, it's part of the geometry. It's not that hard, but you can calculate this part. It's not that hard. Just I give you some easy solution because we are getting out of time and I have to cover a lot of other stuff. If I connect this to this with a straight line, assume that these are a straight line. Yeah, you have a triangle here. Assume that this is a straight line from center of the column, a straight line. How can I calculate the total area of this part from this radius and this arch or arc of the column? How can I find that? Is equal angle based on the radian divided by 2 times r square. This is your r square times this angle in radian divided by 2. That's it. You can find the area of the hole. But you want just this hatch part, not this part. Okay, it's not that hard to calculate this. This is triangle. You have to calculate this part. Yeah, you have to calculate this part, and you know that that's from here to there is your r. That side is a. You know c. A times beta 1, you know a. So r minus a, you know this distance. So in order to find the area of this triangle, this base, yeah, times this height divided by 2. This area minus the area of that part of the column will give you this, the area of the hash part. Yeah, so I gave you the solution. If you like, go after it and try to write the equation for that. Okay. Uh, as you can see, the same equation for the concrete for this part. And in your exam, I'm not going to give you circular column. Yeah, because this must be part of your knowledge from the past. I'm not going to just check you to see if you still have that knowledge or not. But you want to be a good student now and good engineer in future. Go and do it by yourself. Show to yourself that you can do it. It's not that hard for you. Okay. Then as soon as you find that, that's it. The equation should be exactly the same. No difference. No difference. Just a over 2 for this one is not a over 2. The distance from here to here, you have to find that location of the centroid of this part of the circle. So it's not that easy, but based on the integral method, you can find it. Or if you go to the statics book, they gave you this part of the circle. They showed you this CG. Yeah, and because of those, as I mentioned, this is not part of your exam at this for this course here. Okay. Then I gave you another homework, but look at this. I gave you C based on the distances. You can see all these rebar are in compression. The others are in tension. I named them AS1, 2. I didn't show which one is compression. But because load at this side of this center line, so you have compression this side of the neutral axis, tension other side. Remember, if the load was at that side, compression this side, tension other side. If in exam I change the location, doesn't matter. So if I show the point load that this side, that's the center line. It means that compression at this side, tension bottom part. So I can play with this, put that here, here, or here. Then just the only thing that will be changed, the compression part. The equations and the others will stay the same. So I like to see everybody will go after this and will solve this and send that to me, please. And then let me know if you have questions. But before this, go and do that example few times. Please do it. Please do it. Okay. Discussion that's important. I like to let you know that in some code, some parts, you need to know if somebody asks you why the concrete column is percentage rebar is 4%. So based on the code, if you don't know the answer, that's not that good. So if we add steel to the concrete column, we increase the capacity. We have some actually profile inside the concrete column. So for sure it's more than 4%. If it's allowable, why if I add more rebar is not allowable? That's not the point. The point is if you put a lot of rebar when you have this lapis flies, look at this, you can remember from the development lab, when you want to continue the rebar, put them close to each other, and then keep going to the for the column. So in this case, you have double of the rebar, because you have, for example, 4 rebar like this, and for the top part, you have to add more rebar. You have to put another rebar here for this one, another rebar for this one, another rebar for this one, another rebar, at least, to keep going. If you have more rebar between, then you have to add another. So you will make kind of a wall here, and that's not good, because the small and fine material of the concrete can go to other side, and the big rocks will stay here with no mortar. And when there is no mortar, mortar will act like a glue in the concrete. When you put the glue the other side and rocks here, the strength of this column is not that good. So because of that, we don't want to have too much rebar to make that wall, to stop concrete flow everywhere. Yeah, we must have diameter of the bar or 1.5 inches, whichever is greater for the concrete, for the columns. So we need that space because we want the big rocks to be able to go everywhere, and the mortar can stay with the rock. So in that case, based on a lot of tests, we came up with 8%. Yeah, ACI will give us 8%, means that total bar means double of the rebar. So because you have lapis splice location is the worst place of the concrete columns. So 8% is for there. So for the rest, it's 4%. And because of that, the maximum rebar in the column is acceptable 4%. But if we are using these actually new devices, couplers, we are using right now in the field couplers like this. Before it was huge, huge. Right now, about maybe 15 years ago, I can remember we used those, and they were huge. And you can see we have to create 1.5 inches, and because of that, we cannot put them at one location. We install one here, another 2 or 3 feet higher, another here, another every other one. So in this case, we can create that 1.5 inch at least. The concrete can flow. With this case, you can go like a river. Look at this, not that big, bigger than that. So in this case, if you are using kind of this, even over here, you can go with 8%, because there is no lapis splice. The rebar will be added just with the couplers, something like that. So rebar at the other side rebar with no lapis splice. So in this case, we can go with 8% or closer to the 8%. So if somebody asks you why we have 4%, but we can install profile inside the concrete, the answer is the rebar, if it's more than 8%, it will stop following the big rocks to everywhere. It will stay inside and the mortar will go outside. And it's not acceptable to get good result. Is the percentage of the area? Yes, that's 8% of the area. Rho is equal AS divided by BH. Can you remember? Rho is equal percentage of the rebar is equal AS divided by BH or BH, yes, for the column. Okay, so that's the thing that I wanted to share with you guys to make sure that we know the reason why 4% is in the code. Okay, let's go with the diagram that last week I showed you, that was something like this. And somewhere around here, we call that above that is in compression, below that is in tension. Okay, so let me answer. Is rebar allowed to be welded together instead of coupler? No, no. If those are very restricted, very restricted. For the earthquake in high, actually risk zone earthquake, there is no welding allowed. If you have to do the weld, you have to check all single one to make sure that if you pull them to the FY, then just the weld will not be cracked, or the collapse should be in the rebar, not in the weld zone. And because of that, it's not allowed in any column in high risk zone. No, you can't do that. Okay, good question. So in the column, from now on, you can, right now I gave you how to calculate the moment capacity, the axial capacity by hand. As an engineer, you must be able to do it by hand. Imagine you don't have access to this. So how can you design the column? I gave you some information for hand design, and these are based on the code design. Okay, how can we use this? ACI provided a lot of this. It has one handbook, more than 200 of these charts. So each one has this stuff. And just based on this, you have to pick the correct one. For example, this is A5. They call that A5. H, I put this note for you, parallel to E. As you can see, look at this. That's the elevation view, cross section. PN, E. What's the moment on this one? PN times E. So showing MN and they show PN with the eccentricity of E. They are the same. So in this case, the rebar shouldn't be 1, 2, 3, 4, 5 at either side. No, this case is good that whenever you have equal number of rebar at either side. So 3, 3, 3, 3, you can use this. 4, 4, 4, 4, 5, 5, 5, 5, 8, 8, 8, 8, depends on the size of the column. So just equal number of the rebars. Then you can use this. But this case is good for F prime C for KSI, FY 60. If you're F prime C5, it's not good chart. There is another one for you. Go after that. And this is good for gamma equal 0.6. What's the gamma? Gamma is equal. So in the example, you can see that this gamma is equal H. That's the side that is parallel to E, minus 2 cover from center to here, center to here. If I call that, I don't know, D prime and D prime, yeah, to the center. If I call that D prime, okay, H minus 2D prime divided by H. That's your gamma. So if you have 80%, that's not for you, it's 60%. There is another one for that percentage that you want. Yeah, so we have to check this and see if we want to have 4 sides equal or 2 sides rebar. So we have another chart for 2 sides rebar. Okay, so pick the one that you want based on this information and pick the right chart for yourself. Then these are, look at this, 1%. If you have 1% rebar, 4 side equal 1%, means that 1% times B times H will give you the total AS. Go to the chart and pick, for example, 3, 3, 3, 3 means 8 rebar. Yeah, AS divided by 8, pick the size of the rebar that you want. This 2%, 3%, as you can see, up to 8%. Because if you are going to use that coupler, you can go with closer to 8%. You are not using couplers, you are going to use a splice, then maximum should be 4%. Yeah. So this is for PN. Look at this, PN divided by F prime C AG. You have a load, a column. You want to check if that size of the rebar that you consider is good for this load or not. You know PN and MN. So PN F prime C, instead of PN, I can write P, doesn't matter. So PU divided by phi F prime CAG, the same. PN F prime CAG, those are the same because PN is equal PU divided phi. The same as here, Kn, this side is Rn. Rn is Pn, E means Mn. Yeah, Pn times E means Mn. Mn divided by F prime C Ag H. What's the H? Side of the column parallel to eccentricity. Or instead of Pu, you can Pn, you can write Pu divided by phi. It means that Mu. So if you are using Mu, use this one divided by phi F prime C AGH. If you are using Mn, most of the time do because it's external load. Yeah, Pu is external load. Mn is external. Mu is external load. So Pu or Mu, Pu times this is your Mu. You don't need to do anything. Just instead of Pue, consider Mu divided by phi. That's it. If you got it, you got it. So based on the loading, find this number, find that number. For example, one here, go a straight line, another based on the number that you calculated, go and find the cross section. If the cross section is inside the percentage of the reward that you have, or on, that column is capable to carry that load. If it's outside, it's not good. You have to increase the F prime C, or you have to change the size of the rebar, do something to make that good. Okay, another chart, the same as the other one. Look at this, 4 side equal F prime C 460, but instead of 0.6, 0.7. Yeah. So if you have 0.6, but what about 0.65? There is nothing for 0.65. They have 0.6, 0.7, 0.8, something like that. So what can I do for between? You have to use interpolation. Yeah, find for 60, find 0.7, and then find for between them. I'm solving one example for that one as well. Okay, these are different charts. As you can see, this one is the state. Yeah, that's it. Everything is the same, just 0.8. And this is for two sides moment, two sides equal. 1, 2, 3, 4, 5 always. No, it can be 2 and 2, 3 and 3, 4 and 4. That's it. But there is nothing we can use this chart. Again, it has 0.6, 0.7, 0.8. Just I put some as an example for you guys here. Yeah, that's it. Let's solve one example based on this. Right now, we have the knowledge to go after this and find the answer. Okay, imagine we are going to design this column. This is a frame. We analyze that, and we want to use F prime C for case size FY60, and this is our epsilon S. And we are going to design this column. We did the analysis for this structure, and these are the loads that we got. Yeah, we got for load case 1, MLMD, moment caused by dead load, moment caused by live load. P caused by dead load, live load. Yeah, case 1, PL this skips, PD this skips, ML and MD. Load case 2. So we have to find the percentage of the rebar for both cases and pick the maximum, because this column has both cases. So the column must carry the maximum. Yeah, but we can compare these two to see if it's acceptable or not. We have to go through all the required ACI, actually step by step, to check it to see if it's correct or not. Okay, what's the column? Column is 20 by 25, as you can see here. We have eccentricity, E, and this is your PU. Yeah, so H is always parallel to, and what's the E? Is mu for d plus L divided by pu d plus L, or mn divided by mn. Doesn't matter, because this one will get phi, this one will get phi, and those two can cross them out. So n and mn, or mu and pu, all of them will give us, but not mu divided by pn. That's wrong. Mn divided by Pn, Mu divided by Pu will give us the same eccentricity. Okay, we want to check and find the maximum percentage of the rebar, and we know that we want to use the column, yeah, that we know the size of the column. We gave you the size, and we want to have equal rebar at each side. So we know what chart we are going to use. Okay. In this case, let's start with the loading. We know that for load case 1, load case 2, yeah, go with this one. 1.2 dead load, 1.6 live load. That's your PU, ultimate load. MU, 1.2 moment dead load, 1.6 moment live load. That's it, yeah. And we assume that we have 2.5-inch cover from concrete to the center of the bars. Yeah, we assume this. So your gamma should be what? H. H is parallel to E minus 2 times of the D prime, means 2 times 25, 2.5, divided by H, the equation that I gave you. So in this example, we made that simple. You don't need to do interpolation. Just we got 0.8 that we have chart for that. Then calculate Kn. Kn was Pu divided by, forget about this phi, Pn divided by F prime CAG, or Pu phi F prime CAG. Both of them are the same. In this case, we have loading Pu. So Pu, it's better to use this one. Always phi for the column, 0.65. For moment or for axial load, always phi 0.65. Okay. FRMC for KSI, AG 25 times 12, 500. Yeah, that's AG. B times H, 12 times 25. You will get 0.57. What's the RN? MN, MU divided by phi, FRMC, AGH. MU 474 times 12, because everything is inches. A square inch, AG, and H 25 inches. So times 12 to convert that to the inch. If you make mistake, we had in exam that one or two forgot to convert the actually unit, and they got very small numbers. Though then everything is wrong because of the that wrong very small number. So right now we can calculate this for case 1 and do the same for case 2. Yeah. So at the end, we know what chart we are going to use, 0.8, and F prime C4 and Fy 6C. And these numbers 0.57, 0.175. So in this case, we have to go to graph A7. Why graph A7? Let's go and figure it out why. Graph A7, look at this. You can see F prime C4, Fy 60, gamma 0.8, equal rebar either side. So that's the chart that we must use. That's that easy. Then Kn, look at this. Then Kn, we calculated 0.57, 175. Just remember those numbers. 0.57, 175. Okay. 0.57. Look at this. Over is 0.60. 0.58, 0.57 is between this Ku, yeah, Kn, 0.57 is here, 0.5, 52, 54, 56, 58, 60, 0.6. 57 should be between. I will draw one line between those two. Then 1.175, okay, 0.15 to 0.20. 0.15, 16, 17, 18, 19, 20. So each one is 0.01. So 0.175, 0.16, 0.17, 0.75 should be at the center of this. Plot one horizontal vertical line here. The cross section between these two will give you the percentage of the rebar. 1%, no. 2%, no. 3%, too much. Something between these two. So you have to measure this that is 2.5%, 2.4, 2.6, depends on a location that you can measure. Yeah, that's it. This point, cross section of these two, as you can see, it's closer to this side than to that side. Is a little smaller than 2.4%, 1%, 2%, 3%. This one is 2 point something percent. Okay, let's go and see here. 0.0 means 2.4% divided by 100 because that percentage. So your rho is 0.024 or 2.4 divided by 100. Yeah, because 2.4%, 2.4 divided by 100. That's the percentage of the reward. What's the AG? AG or your AG for cross-sectional area is 20 times 25 BH. So your AST rebar should be percentage of the rebar times total area of the concrete, 12 square inches. So we will pick 12 number 9, means exactly 12 square inches. So 12 number 9, it means that each side you should have, let me see, you want to have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Means either side you should have 4 rebar. 4, 4, 4, and 4. That's it. That's it. As you can see, and do the same, go with these two numbers, you will get 1.7%. So which one is more critical? This one. So this is your final answer. If you have 3 load cases, 4 load cases, do the same and pick the maximum percentage. That's your final answer. And then tie bar, if we use number 3 up to number 10 vertical rebar, we are using tie bar number 3. And above 10, we should go with number 4 at least. If you go with number 4 for number 10 and 9, it's good. But if you go for number 11 with number 3, it's not good, it's not acceptable. At least number 4 for more than 10 and number 3 for less than 10. Not number 2, never number 2, number 3 and above. A spacing maximum of those 3, and we know how to calculate this. That's it. If you got it, you got it. That's the column, and I gave you 20 and 25 with this eccentricity with one load, and I asked you, I gave you the assume the rebar covered 2 inches. Yeah, I wanted to make that easy for you guys, so you can calculate that one for homework. So far, I gave you 2 homeworks for this week. Another example. We want to design this column in this frame. After analysis this, we got PU and MU. So there is no dead load and live load. We had, but we find that total. So in this case, we want to calculate the size of the column. We don't know B, we don't know H. We don't know. But we know PU and MU and other stuff. And we want to calculate the find the rebar and size of the column. Like always, assume something. We know the percentage is 4. So we assume that, okay, rho G is 3%. You can go with 2%. If you have limits as before for the beams, the architect will give us the limit. So based on that limit, we cannot go with any size that we want. So we have to play with this, go with 3%, then you can see the size are too small. Then you will go with 2%, and then 1% is too big. So you can figure it out by yourself. Yeah. So just learn this, how to use this, then you can play with this and change the size of your column. Okay. We assume that 6% is good, less than 4%. Okay. Then because we still have 2 unknown, B and H, I can't calculate that. I can't design like beam. I will pick another one. So in this case, because we know the answer that 25 is a good number for this, we went with this. But if you go with 20, then you can see, oh man, your B is big, too big. You don't want that. It's not good based on the architect limits, architectural limits. So you have to change that and play with this until you get the number that you want. So this will give us how to do it, and then you can play with these numbers and get different numbers. That's it. Okay. So right now we know percentage, we know H, but I have no idea about B. How can I calculate B? Okay. So for the H, for the gamma, H minus 2 cover divided by H. So 25 minus 2.25 divided by 25.8. So we need something like this with F prime say 4 and Fy 60. So we have to go to A11, both sides rebar. We don't want at both sides. In this case, we want to, how we can go with this, I will talk about this later. But when you know that you want to go with this, you can go with the 4. Yeah. But whenever you go with 4, this rebar here will not work that well. Just these two will give you the maximum capacity for the moment at this direction. The rebar here, you will get less tension, less compression, less. So those will not carry that much load. So you will lose rebar. It's better to go with 2. But if you have moment at both directions, so your P is not here, not there, it's somewhere around here. It means that you have moment around X, you have moment around Y. So in that case, the base case is equal rebar for sides. So that's the answer. If somebody in future asks you, when are you going to consider rebar as 4 sides for a column? The best answer is when we have eccentricity at both direction. Means we have moment around X and moment around Y. So in that case, the best answer is equal rebar. So when is the best for the moment rebar at 2 sides only? When we have moment at one direction only. So the rebar should be perpendicular to the eccentricity. So if you have eccentricity this side, rebar should be here. If you have eccentricity here, this side, you should have rebar these 2 sides. Please put note for yourself. Not in the book. These are outside of the book. These are your base of your knowledge, how to pick the best rebar actually arrangement in the column. So you can find them in somewhere. Put a note for yourself. Okay. So in this case, we are going to consider some case like this with gamma. And how can I find eccentricity? Look at this eccentricity. Mu divided by Pu. But Mu is foot keep times 12. That's eccentricity. And whenever you want to find B, that's the process. Okay. Then find E over H. We need to know this. E, we calculate 12.3. H, 25, parallel to E. Then go and use that graph A11 based on this information to find things, because we know the percentage. So percentage is not that important for us right now. The problem is finding B. So what we did, we calculated E over H. And we know the percentage of the rebar. Okay. This is the percentage of the rebar, 3%. Look at this. This is your 3%. And look at these lines. These lines are E over H. You can find them on all charts, all of them. So whenever one of the element dimensions are not clear and we have to find them, you have to do whatever I'm doing right now. Okay. We use 3%. And we use E over H. Look at this. This is 0.9, 0.5, 0.4, 4, 4, 4, 6, 4, 8, 4, 4, 6, 4, 8.5. So 49 it should be between this and 48. This is 48, 49, 50. So from 0, I will go to between those two, 49. This is the line. Then intersection with 3%. Yeah. And plot one horizontal or vertical, doesn't matter, you will get the same answer. But we went with the horizontal. Read Kn. Kn is Pu phi F prime C Ag. Read this number. Yeah, read this number. That's it. Then the problem is solved. Okay. Based on the interval E over H 0.49 and 3%, we read that Kn is 0.51. Okay. Based on this, I know that I can rewrite that the Pu divided by phi F prime C times BH is Kn. Yeah, times Ag. Ag is BH. So that's the equation for Kn. Kn is equal Pu divided by phi F prime C Ag. Then instead of Ag, I will write BH. Then I will change the location of B and KH. B over here, KH over here, Kn. Kn over here. Then plug in the numbers. Pu 0.65 F prime C always, 0.65 always for phi, F prime C times Kn, H. That's the minimum required B. So if we go with 15 times 25, we should be good. That's it. As you can see. Then ASC, what's the ASC required? 3% of 15 by 25, because we came up with B15. So we will get 11.25. Then we will use 8 number 11. It's almost 12.48. 8 number 11 means 4 at this side, 4 the other side. That's the design for this column. As you can see, it's very easy to actually instruction and is the design. Any question? Let me read one chat. Why is there 2 phi in the equation of Kn? Let me see, there was 1 phi, not 2. Let me show it to you. Look at this. In Kn is equal Pu divided by phi F prime CAG. Let me read that again. Even after converted to Pu. Look at this. Whenever you have Pu, you have P, you have phi. Otherwise, if it's Pn, then there is no phi. Yeah, just remember. Let me go back to this equation. Look at this. Pn F prime CAG or Pu divided by phi F prime CAG. Whenever you are using Pu, you must have phi. If you are using Pn, there is no phi. If you are using Pn, there is no phi. Or Mn, Pn times E means Mn, no phi. If you are using Pue or Mu, you must have phi. Did I give you the answer?
Professor,
Okay, thank you. Yes,
for columns, so phi will always be 0.65.
always.
Professor, I had a question.
Yes.
Can you explain again what was AG and how we got that?
Ag is cross-sectional area of the column. Yeah, it's 25 times B times H. Yeah, B times H is cross-sectional area of the column, Ag.
Okay, thank
Yeah,
you.
so you have 15 by 25. That's total cross-sectional area.
Got it. Thank you.
Okay. 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 Any other question? So, is there any question? No question? You got it completely? Perfect. Perfect. So actually, tomorrow is a holiday, and we don't have a class based on the school. There is no class for tomorrow, and today I'm going to give you lab. For tomorrow, we don't have lab, but the next week I will give you 2 labs, because on Tuesday they can go one actually lab more than the Wednesdays. So next week on Wednesday, I'm going to cover 2 labs instead of 1. And there is no lab for tomorrow, but today we have lab. Those that they have class lab tonight, please stay. As soon as everybody left, if you all agree, I can continue on the lab. Then you can, I can let you go sooner, except those that they want to actually talk about the exam and see their talk about all those actually mistakes they might have in their exam. So if there is no question, I'm done for today. Thank you, and see you next week.